Welcome to today's paper reading. Today's paper is titled, Attention as an RNN. This paper, titled Attention as an RNN, is authored by Feng and colleagues from Mila and Borealis AI. It is currently under review as a preprint. The abstract highlights the significant impact of transformers in sequence modeling, leveraging GPU parallelism for high performance. However, the computational expense at inference time restricts their use in low-resource settings. The authors demonstrate that the attention mechanism can be conceptualized as a specialized RNN, capable of efficiently computing many-to-one outputs. Despite this, updating these models with new tokens remains inefficient. To address this, the authors introduce RNN, an attention-based module that combines the benefits of parallel training with efficient updates, requiring only constant memory for inferences. Empirical results show RNNs comparable performance to transformers across various sequential tasks, while being more efficient in terms of time and memory. The advancements in sequence modeling are significant due to their applications in various fields such as reinforcement learning, time series classification, and time series forecasting. However, transformers, despite their strong performance, face challenges in low-resource domains due to their quadratic scaling in memory and computation. This issue is particularly pronounced in long context settings common in time series data. To address these limitations, the authors propose a new approach that views attention as a special type of recurrent neural network, RNN, and introduces a new attention formulation based on the parallel prefix scan algorithm. This leads to the development of the RNN module, which is designed to be both computationally efficient and capable of handling new tokens with constant memory requirements. Empirical results show that RNN achieves comparable performance to transformers while being more efficient in terms of time and memory usage. Recurrent neural networks, RNNs, are designed for sequence modeling, processing data iteratively by computing hidden states. This makes them efficient at test time but suffers from a lack of parallelizability. Transformers, which use an attention-based mechanism, have replaced RNNs due to their parallelizability but require quadratic computation with respect to the number of tokens. The attention mechanism retrieves information from context tokens using query, key, and value matrices, designed to leverage GPU parallelism rather than being iterative. In this section, we explore the methodology of viewing attention mechanisms as recurrent neural networks, RNNs. Specifically, we discuss how attention can be conceptualized as an RNN, and how this perspective applies to popular models like transformers and perceivers. This view reveals challenges, such as the inability to efficiently update with new tokens, which traditional RNNs like LSTMs can handle. To address these challenges, we introduce an efficient method for computing attention as a many-to-many RNN using the parallel prefix scan algorithm. This leads to the development of the RNN module, which can be trained in parallel and efficiently updated with new tokens at inference time, requiring only constant memory. This makes RNN significantly more computationally efficient than traditional transformer models. Figure 1 illustrates how attention mechanisms can be conceptualized as a many-to-one recurrent neural network, RNN. The query tokens serve as the initial hidden states of these RNNs. In Part A, the conventional attention method is shown to compute only the final output, thus functioning as a means to derive the many-to-one RNN output of attention. Part B depicts transformers' self-attention, which employs the input tokens as the initial hidden states. Lastly, Part C shows perceivers' cross-attention, which utilizes input-dependent latents as the initial hidden states. This figure highlights the transformation of attention mechanisms into RNN structures, providing insights into their computational processes and initial state configurations. Figure 2 illustrates the RNN cell for attention computation. The cell iteratively computes AK, CK, and MK from AK1, CK1, and MK1, encapsulating the recurrent computation of attention. The initial hidden state for the RNN cell is set to A0, C0, M0, Q equals 0, 0, 0, Q, where Q is the query vector that is carried over in each iteration. This approach allows for the efficient computation of attention as an RNN, providing a stable and numerically robust method. Figure 3 illustrates the concept of computing attention as a many-to-many RNN using a parallelized method. This method leverages the parallel prefix scan algorithm to efficiently compute attention outputs. The associative operator circle plus is applied to three tuples of the form ma, yue, wa to facilitate this computation. This approach results in an efficient parallelized method for computing attention as a many-to-many RNN, addressing the limitations of traditional methods. Figure 4 illustrates the stacking of RNN models for sequence modeling. RNN, which stands for Attention as a Recurrent Neural Network, leverages the parallelized many-to-many formulation of attention. Unlike transformers, RNN's query token is learned during training, and it outputs an aggregate of the inputs. This method makes RNN more efficient, requiring only constant memory and not needing to store all previous tokens, unlike transformer-based models. The objective of the experiments is to compare RNNs with transformers in terms of performance and resource usage, specifically time and memory. This comparison is conducted across 4 problem settings: reinforcement learning, event forecasting, time series forecasting, and time series classification. A total of 38 datasets are used, with the majority being real-world datasets. These datasets are divided among the problem settings as follows: 12 for reinforcement learning, 8 for event forecasting, 8 for time series forecasting, and 10 for time series classification. For each dataset, the models are evaluated with 5 seeds. To ensure a fair comparison, RNNs replace transformers in domain-specialized models, and the same set of hyperparameters is used for both RNNs and transformers. Table 1 presents the results of a comparison between RNN and transformer models and reinforcement learning tasks, measured by the D4RL score. The scores are shown for 12 datasets across 4 environments: half-cheetah, ant, hopper, and walker. Each environment has 3 types of datasets: medium, medium replay, and medium expert. The table highlights that RNN models achieve competitive performance with transformers, with some instances of RNN outperforming transformers. Notably, RNN's ability to process new interactions in constant computation due to its RNN nature makes it particularly suitable for reinforcement learning scenarios. Table 2 presents the results of event forecasting using RNN and transformer models across various datasets. The datasets include Mimic, Reddit, Stack Overflow, Uber, Wiki, Mook, Sin, and Taxi, with Sin, Uber, and Taxi lacking marks/labels. The performance is measured in terms of accuracy, ACC, negative log likelihood, NLL, and root mean square error, RMSE. The table highlights that RNN performs comparably to transformers, showcasing its efficiency in processing irregular event streams. Table 3 presents the results of time series forecasting using RNNs and transformers. The models are evaluated on 8 real-world datasets with metrics mean squared error, MSE, and mean absolute error, MAE. The evaluation is conducted with a future prediction horizon t set to 192, given an input length of 96. The table shows that RNNs perform comparably to transformers across all datasets, with RNNs demonstrating efficient processing capabilities, making them more suitable for time series-related domains. Table 4 presents the results of time series classification experiments comparing RNNs with transformers. The objective of these experiments was to predict the label of a time series, a common task in applications like pattern recognition and anomaly detection. The study utilized 10 popular datasets from the UEA time series classification archive, showing that RNNs perform comparably with transformers across all datasets. The table provides accuracy metrics for each dataset, highlighting the performance of both models. Figure 5 presents a comparison of computational resources between RNNs and transformers, specifically focusing on memory usage and cumulative time required for processing sequences of tokens. On the left, the memory usage comparison shows that transformers, when using KV caching, experience a linear increase in memory consumption as the number of tokens grows. In stark contrast, RNNs maintain a constant memory footprint, regardless of the token count, indicating a significant efficiency advantage. On the right, the cumulative time comparison reveals that while transformers exhibit a quadratic growth in cumulative processing time, RNNs demonstrate a linear growth. This further underscores the computational efficiency of RNNs over transformers in sequential processing tasks. The models closest to RNN, such as RWKV, RetNet, and linear transformer, propose linearizations of the standard softmax-based attention, allowing them to be formulated as an RNN. However, these models encode an exponential factor that biases tokens based on their timestamp, limiting their applications. In contrast, RNN leverages an exact reformulation of softmax attention as an RNN, enabling the model to compute the weight of each token. Feng et al., 2023, demonstrated that attention can be computed recurrently, while Raid and Stats, 2022, introduced a recurrent formulation of self-attention. Katharopoulos et al., 2020, showed that transformers with a causal mask can be viewed as an RNN. RNN introduces a new attention formulation based on parallel prefix sums, achieving competitive results with transformers while being more efficient. The problem of computing prefix scans/sums has been well studied, with various efficient parallelized algorithms proposed. Hillis and Steele, 1986, outlined a method requiring log2 n sequential steps and O n log n overall computation, while Ladner and Fisher, 1980, use more sequential steps but only perform O n overall computation. For a more in-depth introduction to parallel prefix sums algorithms, refer to Blalock, 1990. In this work, the authors demonstrated that attention can be formulated as a recurrent neural network, RNN, contrasting with the conventional parallelized method of computing its many-to-one RNN output. They extended this formulation to show that existing attention-based models can also be represented as RNNs. However, unlike traditional RNNs like LSTMs and GRUs, these methods face efficiency issues when updating with new tokens. To address this, the authors introduced a new parallelized method for computing the many-to-many RNN output of attention, based on the parallel prefix scan algorithm. Building on this new formulation, they introduced the RNN module, which can be trained in parallel like transformers and efficiently updated at inference time, requiring only constant memory. Empirical results showed that RNNs achieve performance competitive with transformers across 38 datasets in various sequential data settings, and are significantly more time and memory efficient. Thank you for watching.